Back today, and we're going to talk about basically continue our discussion about quantifying uncertainty and error, and basically doing a comprehensive error analysis, which we're going to work with in this course. So last time we identified bias error, precision error, illegitimate error, and sometimes bias, sometimes precision. We are going to be typically and more we are going to be concerned with primarily bias and precision error when we're evaluating our experimental data. So one quick thing, you'll typically deal with experiments that are either two broad classes, single sample experiments or repeated sample experiments. A single sample experiment is typically done when these are really much more uncommon, and they really only occur when the measurement that you're trying making is extremely, extremely difficult, really, really expensive, economic reasons and practicality reasons, or where multiple experiments cannot realistically be conducted. So you kind of want to think about like Large Hadron Collider, kind of those types of experiments where we can't run 10, 15, 20, 30 measurements on those samples. So when you do single sample experiments, the error analysis that you're going to conduct is a little bit different, but we're going to kind of discuss that. You'll have to kind of rely on your experience, essentially as an engineer. You're going to have to do a lot of bias error analysis, and so it's a different type of error analysis that goes into it. But most commonly, and definitely in this course and almost always in industry and academia, we're going to be working with repeated sample experiments. So a sample is an individual measurement of a specific quantity. So you're going to measure essentially like the strain or the frequency or the temperature of material multiple times. You're going to kind of look at the distribution of those measurements. In a single sample experiment, we can't quantify any precision error because there's only one measurement. So that's kind of the big differences here. So in this course, we are not going to do percent error. We are going to calculate total uncertainty. This is the metric that we care about, not R-squared, not percent error, never put percent error in this course, total uncertainty. So the total uncertainty in some variable, some measure and X could be volume, pressure, stress, temperature, strain, frequency, cyclic frequency, omega, et cetera. But it will be basically the square root of the total bias error contribution and the precision error contribution. So we're going to talk more into, and we're going to start with calculating precision error first. In lecture 5, we're going to talk about how you calculate the bias error, propagating error. That'll be a little bit more difficult, but we'll get to that in a bit. One key assumption in this equation is that the bias and precision uncertainty are both independent sources of error, so they're not related. And we're using the same confidence level when calculating that total uncertainty. So you'll understand a little bit better about that what that means when we kind of do some examples. So actually, speaking of which, let's start with a fairly straightforward example. So Pepsi, not sponsored, is redesigning plastic bottle. So they're using PET, polyethylene terephthalate. It has a TG, a glass transition temperature, where we go from glassy to rubbery behavior, approximately 81 degrees C. So they measured it 45 times, and they found the average TC to be 81 degrees C. So excellent. But they want to market this bottle as more mechanically stable than its competitor, and claims that with 95% confidence, TG, the new bottle, would be within plus or minus 0.1 degrees C of the mean TG. So they give you that the precision error is 0.01, the bias uncertainty is 0.05 C. With both of these with 95% confidence, would you advise Pepsi to move forward with their marketing campaign? Well, it's one of the key parts in diagnosing this problem is we need to make sure at a 95% confidence interval that your TG is going to be 81 degrees C plus or minus 0.1 degrees C. So this needs to be our total uncertainty U sub X, which here would be U sub TG. So in this problem, we say that both of these, so both are working at the same confidence level. It doesn't say anything about the sources of error being, dependent on one another. So we know that precision uncertainty is this. We know the bias uncertainty is this. Plug and chug into the equation, and you'll see that we're fine. We can meet, we're actually basically almost a factor of 2 better than what we might anticipate. So we can move forward with that expression, and you can kind of double check your answer in Mathematica right there. But we can go ahead and move forward with this marketing campaign. So you will not get an example that easy in class, but just to start you off with something simple or a little relatively simple and straightforward. So speaking of kind of these multiple measurement experiments, we want to be able to distinguish kind of two key concepts. So distribution of error and the population from which a sample is taken. Really, sample versus population, what we're going to talk about. Distribution of error, we're going to kind of look at these when we take measurements, and that's going to be kind of calculated within this precision error. It's going to be related again to the probability distribution, which we're going to introduce in this lecture. Finally, Gaussian, the width of that Gaussian, your standard deviation, that gives you some idea about the distribution of that error. But I think a key difference is this idea of a population and then a sample. So we will never really know for a temperature. We don't know the entire population of those measurements. We don't know what the real population mean and that distribution is. But we are going to draw samples, and the larger or the more measurements, basically, the more samples that we gather, the more measurements we make, we can infer, and we'll have actually a better confidence and a better certainty, a less uncertainty about the characteristics of the larger population which we're drawing those samples from, right? Because we can't measure every single place in a room what the temperature is. So there's this large populations of measurements that we can make, but we're only going to take a limited sample measurements. And typically, again, we're going to be working with, we're going to assume the probability distribution is going to be Gaussian. So we could estimate from a smaller sample the kind of true mean of the larger population with some degree of, with some uncertainty or some degree of confidence. So these confidence intervals. So just to kind of give you an example of sample versus population, let's imagine basically this handful of marbles, or this infinite bag of marbles, or not infinite. Actually, we're going to create basically we're going to create our own bag of marbles. So I have a bag of marbles, 10,000 of them, and I am going to have a mean. The mean size of those marbles is 10 millimeters, and it is going to have a standard deviation of 1, which I'm drawing from. So these are all, I actually know my population here, which is not common when we're working with, usually we will never know our population, but in this case, we know our population, but we'll never measure all of these marbles necessarily. So we don't want to, and we definitely don't want to measure those marbles, but let's kind of take a look at let's take a look at our bag of marbles, and that looks to be normally distributed, Gaussian, centered around 10. So if I take the mean of that entire population, it's centered basically around 10. Standard deviation is around, pretty close to 1, a little bit less. Again, it's randomly generated. So if I grab one sample, so I'm going to randomly grab one sample, one marble from my bag. That is a big difference, right? 9.1 versus 10. That's not really accurately kind of characterizing my larger population, right? But if I start to increase my sample size, so instead of 1, let's grab 10, and then let's calculate the mean. I'm getting pretty close now, right? What if I grab 50? The approximation, that's a bad example. That's why you have to randomly grab even more. My approximation is getting a little bit better. You always have to check this. Don't randomly grab. Let's say I grab 500, for example. I'm going to change this right here. Much better, right? Then say if I grab 15. So if I grab 15, again, not as essentially, I'm not getting really a good distribution. So the key thing here is the larger your sample, the closer you're going to get in terms, or the more certain you're going to get in what you can infer about your larger population, even if we don't know, and most of the time we will not know basically what the distribution looks like. So that distribution does not have to be Gaussian, and a lot of times it will not be Gaussian. The population basically probability distribution. So that's kind of a key thing. So many times you will find that the population is Gaussian or normally distributed, but there could be populations that are really weird looking here. We are going to invoke a really critical theorem in statistics, the central limit theorem, a little bit later on. That's going to allow us to really not care, because we're going to develop an entire set of procedures in this lecture about how we can kind of estimate kind of the population and the uncertainty on our samples. But we're going to kind of depend on that we're using or working with some normal distribution. But the central limit theorem is going to allow us to not care about what our population probability distribution looks like, and we could still use kind of our analysis tools here. So that's going to be a bit fun, and it's a fun mathematical demonstration a little bit later on in lectures to come. So when you're drawing a sample, your n, the sample size, is always going to be much, much, much less than the population. And we're going to see that our sample size is large, or like good enough to approximate, like our population if n is greater than or equal to 30. We say that's a large sample. If n is less than 30, we are small sample. But more on that a bit later. So in this course, we are going to look at basically histograms and different probability distributions that we're going to work with. So we are going to work with a Gaussian and normal distributions. This is the z-table. We're going to look a lot about that here. There's some kind of unique characteristics. It's symmetric. We're going to use a z-table for calculations. You can also integrate as well. We're also going to use, this is valid for large samples. So this is valid for n is greater than or equal to 30. For a student t-distribution, n is less than 30. Again, symmetric, approaches Gaussian as you increase your sample size, but it's used primarily for small sample size, small data sets. And then finally, our chi-square distribution is not symmetric. It's going to have this kind of right-skewed, I'm horrible at drawing that, this guy. It's a right-skewed kind of distribution. It is not symmetric. We're going to check essentially our goodness of fit for our different distributions. So next time we're going to look at one of our first probability distributions, specifically the probability density function, our Gaussian basically function, and we'll start to calculate and do some nice examples. So I will see you all next time, and we'll start to do some more math and work problems. Thanks. See you next time. Bye.